It may be that intelligence is rare in the cosmos, intelligence as we have defined it. Because if you look at the fossil record, look at the portfolio of life that has lived and thrived on Earth, there are a lot of features of life that many different species have in common. For example, locomotion is a pretty common talent. In fact, we have creatures on Earth with no arms and no legs, and they still manage to move. We call them snakes. So locomotion, they figured out how to move even though they don't have arms and legs. Trees haven't yet figured out how to move. But what we have is evidence of features in life that apparently are really good for survival. The capacity to receive information at a distance. That would be the smell, hearing, sight. Sight is a very common feature in animals. In fact, there are certain expressions of sight that happen independently of each other. That's how valuable this was as a tool for survival. The fly eye has nothing whatever in common with the vertebrate eye, itself having nothing whatever in common with the octopus eye. Yet they are all eyes and they all see. Let's look at intelligence. Intelligence, as we have defined it, has shown up nowhere in the fossil record, which tells me that intelligence can't be all that important for survival. Otherwise, it would have been there in the fossil records. It would have been there manifested multiple times throughout life, but it's not. In fact, you can continue this to its extreme and say it may be that intelligence is just the right thing to have to render yourself extinct.
The Fermi paradox is a captivating and perplexing question that arises when considering the vastness of the universe. It stems from the idea that, given the sheer number of potentially habitable planets in the cosmos, we should have already encountered evidence of extraterrestrial civilizations. However, to date, we have found no conclusive signs of intelligent life beyond Earth. One intriguing way to approach the Fermi paradox, like how Professor Tyson described, is by considering how intelligence, a trait often viewed as advantageous, might paradoxically pose a disadvantage to a species' long-term survival. While intelligence has enabled us humans to create advanced civilizations and technology, it has also introduced existential threats and complexities that could lead to our own extinction or hinder the longevity of other intelligent species in the universe. But before we delve deeper, it might be wiser to gain a comprehensive understanding of the origins and evolution of Earth.
I would bet that when you took biology class, and you learn the age of the Earth 4.5 billion years ago. And then you look at the earliest evidence for life, fossil evidence of life on Earth. Then you get about 3.5 billion years. Subtract those two numbers, get the difference between those two numbers, and that's the time clock from beginning to the first evidence for life. That was about 1 billion years out of the 4.5 billion years that Earth has been here. So that's pretty quick. It happened in like the first 20% of the life of the planet. Now, since the time we all took biology, we have found fossil evidence of life farther back in time than 3.5 billion years. It now goes back to 3.8. There's some evidence it might even reach 3.9. So we have shrunken the time available for life to have formed on this Earth. That makes it more likely. If the faster life kicks in from a pool of just random chemicals, not random, they're the chemicals of the universe, the faster that happens, the more confidence I have that life is something that would happen just given the right soup. We then learned, when computers got good, better than they once were, that the early solar system didn't just simply make the sun and the planets. There was debris all scattered in interplanetary space. And that debris slowly got vacuumed up by the gravity of the respective planets. That would not have been a pleasant occasion on the surface of those planets. Because to vacuum it up simply means you're getting slammed by the kind of asteroid that took out the dinosaurs, except you're getting that monthly. And you can calculate what the temperature of Earth's surface would have been. And it would have been higher than what would allow complex molecules to form. Because at high temperatures, you break apart molecules. So, what our computer models show is that this period of bombardment, period of heavy bombardment is the official phrasing, lasted 600 million years. So it's not fair to start the life clock at 4.5 billion years ago, because life had no chance of forming when the surface of the Earth is molten. Wait for things to cool down. When there's a chance that carbon can run its magic, then you start the clock. Now you're going from 4 billion years ago into 3.8 billion years, and you have pinched down to 200 million years. Down from 1 billion years that was imagined just a generation ago. And that is further evidence that practically the earliest life could have formed, it did. So just because we find it hard to do in the laboratory doesn't mean nature found it hard to do as well. And the idea that it's hard for nature to do because we can't figure out how to do it yet, that itself is an inexcusable expression of human ego.
The relatively swift emergence of microorganisms on Earth once the planet became stable offers compelling insights into the potential commonality of life in the universe. Earth, as a cosmic example, underwent a period of extreme environmental turbulence during its early formation. However, as conditions stabilized around 3.5 to 4 billion years ago, life in the form of simple microorganisms appeared relatively quickly. This rapid emergence of life on Earth suggests that, given suitable conditions, life may have a propensity to arise. The prevalence of basic organic molecules on Earth provide evidence that life can be resilient and adaptable, even in the face of challenging circumstances. The Fermi paradox invites us to consider whether these principles might extend beyond our planet. If life could develop on Earth relatively swiftly once conditions were conducive, it raises the tantalizing possibility that similar processes might occur on other habitable planets scattered throughout the universe. This perspective underscores the idea that while complex, intelligent civilizations may be rare or face significant hurdles, simple life forms like microorganisms could indeed be common in the cosmos.
And if you could look at the element budget of life, hydrogen is number one, as expressed in the water molecule. The number two in the human body is oxygen. Number three in the human body is carbon. 4 is nitrogen. 5, you find on all lists, is other. You go into the universe, number one ingredient in the universe is hydrogen. That was true in life. Number 2 ingredient in the universe is helium. Next in the universe is oxygen. Next, carbon. Next, other. We are 1-for-1 matchup with the most abundant ingredients in the universe. Of these, carbon is the most chemically fertile element in the entire periodic table. You can make more kinds of molecules with carbon than all other molecules combined. So, if you were going to experiment through the forces of nature with complex chemistry, and you had to pick an element to base it on, carbon is your man. Given what carbon is capable of doing, perhaps we shouldn't be so surprised that there's life, because we are carbon-based life. We're just another one of the things carbon has rolled up its sleeve. Maybe life is inevitable, given the abundance of carbon and oxygen and nitrogen and hydrogen in the universe. I'm not given any reason to doubt that the formation of life from out of chemical soups brewing either in our solar system or across the galaxy or the cosmos itself, I'm not given reason to believe that that should be a rare phenomenon.
In 1961, Dr. Frank Drake, an American astrophysicist, made a significant contribution to the field of astrobiology and the search for extraterrestrial intelligence by devising a mathematical framework known as the Drake equation. This equation was a pioneering attempt to quantify the likelihood of the existence of extraterrestrial civilizations within our Milky Way galaxy that could potentially communicate with us. The Drake equation served as a groundbreaking tool to stimulate scientific discussion and guide the systematic exploration for extraterrestrial life. It provided a structured way to approach the question of whether we are alone in the universe, and if not, how many technologically advanced civilizations might be out there.
It turns out that if you created a robot that could use resources on the planet it lands on to replicate itself, so to make 2 robots, and then send one robot off to another planet, so then they then make 2 robots, and if you keep this up, you can populate the galaxy over hundreds of thousands, millions of years. You can significantly populate the galaxy. And this led to what was at the time known as the Fermi paradox, because any alien who could do that would have done that by now and easily have populated the entire galaxy in the time the universe has been around. So where are they now? How come they're not among us? Maybe we are they.
Thanks for watching. If you enjoyed this video, please consider subscribing to our channel and checking out more of our content.